Hi, my name is Brian Clowers. I'm an associate professor in chemistry and also the Boeing Distinguished Professor in Science and Math Education here in the College of Arts and Sciences. I'm also a PNNL joint appointee, which I have strong ties to that institution as I did a postdoc there and also was a staff scientist until 2013 before coming over to WSU. This is the first time and the last time that you're going to see me in a tie. These days I've been spending some time at home with the kid, which is obvious, but still trying to keep things going at the university, and also have a range of professional affiliations where I still serve as both as part of the editorial advisory board and also as a short course instructor for their annual conference for the American Society for Mass Spectrometry. I also participate as the treasurer for the International Society for Ion Mobility Spectrometry and also teach the short course at those annual conferences when they do occur again in the future. We have a range of research support. We've been pretty fortunate over the last couple of years. We have a couple of grants from the NIH, NSF, and also the National Nuclear Safety Administration. And these cover a wide range of topics from applied to fundamentals. I won't have a chance to give you an idea of all of those areas today, but these are some of the members of our research group, and we are surely looking to add some new people to that group in the fall. Some of the past group members are listed down here. They have moved on. Some of them work in industry for instrument companies. Others have gone to national labs. Kelsey here, she's actually moving on to go on to med school. So there's a range of different options following graduation. The research program in my group covers a wide range of areas from the fundamental to the applied. We look at ideas related to signature development in forensics, whether it be chemical, nuclear, or microbial. Oftentimes we wind up using mass spectrometry and other types of analytical separations to get at those particular problems. Recently we've been funded for some work in gas phase kinetics, looking at how different ions cluster in the gas phase and how we can exploit that for analytical gain. And then we also rely pretty heavily on ideas of experimental design, statistics, and other new algorithms that can help us get more information in a shorter amount of time from the measurements that we make in the lab. We also spend a fair bit of time on instrument development. I know this is kind of not as large, but it is something that it supports the ideas that are related to chemistry. But it's really nice to see an idea go from, really basic ideas and move them on into the applied practice. Again, the primary focus, though, is analytical separations. I'll introduce you to an idea of ion mobility spectrometry, which is the core tool that we use in our lab. So here's the general separation scheme in ion mobility spectrometry. It's a gas-filled chamber. This can be atmospheric pressure or a reduced pressure. And we have an electric field gradient that's applied here where it pushes ions through this tube. And based upon the fundamental interactions between an ion and the neutral, we get this orientationally averaged cross-section. And these differential interactions give rise to these separation. So you're most likely familiar with these type of separations for narcotics and explosives detection in airports, but they also have a wide range of other separation utility in metabolomics, proteomics, and other types of fields. Recently, we've spent a fair bit of time developing an open source high-performance ion mobility system. And so here's a schematic or an image of one of these, but also here's ways that we can construct these. They're relatively simple to construct, and we have a fair number of them in the laboratory. And so this is an opportunity for students to build these and have a variety of them so they can go through and try different experiments with relatively little cost. And so these have been adopted by a wide range of individuals, not just in the United States, but across the world. And this is one of had the fortunate opportunity to build one of these for the Army and take it down there to Redstone Arsenal in Alabama. And I got to see the Saturn V rocket, which was pretty fun. In terms of the research focus and student development, I recognize that a lot of times the students coming into my laboratory may not have the skill set or exposed to some of the ideas that we focus on. And that's fine, but we try to, again, work on ideas of gas phase ion chemistry, working on ion mobility and mass spectrometry. We focus a lot on experimental design and really trying to focus on challenging assumptions. So trying to understand what it is you know, how you know that, and is the measurements that you're making actually getting at the question that you're after. And then the other big one here is this idea of failure as a workflow. As I mentioned, we have a range of these different devices that we build in different sizes. So this is a lower pressure system that is extended to ultimately about 1 meter long. And the idea here is that we're trying to have the ability for students to work on a wide range of different instrumentation, not be reliant on a single piece of instrumentation to answer a chemical question. So this idea of failure as a workflow is pretty important, but a key thing here that should be in here is safe failure, right? That's the thing that because we oftentimes work with high voltage and lasers and things of that nature to probe the different types of chemical species. Another thing that's very important in our research group is this idea of group dynamics and how that arises and how different students interact with each other, both to support each other in the time in graduate school, but also in their research endeavors. And so here's an idea, students when they come in, they oftentimes don't have any idea how to assemble these things, so try to give them simple projects to get some experience building these different types of instruments, and also other types of skills that need to be developed. So here's an example of Nate showing Pearl how to do some work in the machine shop. And now don't let Pearl's face fool you. She does like to smile. She just got off guard there when I caught them in the machine shop. So this brings me to some of the other skills that students learn in my group that fall outside of the traditional role of chemistry. We've spent a fair bit of time learning how to solder. This is an important skill for some of the work that we do in the lab. This allows you to fix your instruments and also build new ones. We do a fair bit of coding and trying to work on physical computing, so how you can interface with your instrument and how you're going to collect data. Developing new relationships with your devices, so using your computer as a tool, as a computational tool, as a modeling tool, as a design tool. And so these are things that some students, it's a new concept. Some of the data that we can collect gigabytes per hour easily, and that's not something you can sort through with an Excel sheet. So to give you an example of one of the design processes, here's an example of an instrument that I'll describe here in a moment. These are the different chambers. It's a small vacuum chamber. And what you're seeing here is a cross-sectional view of these ion focusing devices that we can put into a separation device here. And so this is the general concept here. And then, as you can see, we take these devices that we've designed in a CAD program, and then we can put them into practice. So taking those from design phase into the simulation phase, and then ultimately into the construction phase here. And so we have an ion focusing device. Our ions are generated over here off the screen, and they can move through into these devices where they get separated into these small boards. So this is some work that we've recently had funded by the NIH, and it's a technology development program. But the idea is that we have these small little boards here, and they have these very, very, precise structures that have been developed, and these are printed circuit boards. And so we're leveraging that economy of scale and the precision manufacturing capabilities. And so what we can do is we can take these two devices and we can then put them in these coplanar arrangements. And what this does, and once we apply these an electric field to these in a very precise way, we have this track that the ions can essentially flow through. And then what happens is that the ions get trapped in the center. And so this offers a very interesting idea in terms of both collecting and focusing molecules, and then also moving them back and forth around these different devices, as I'll show you here in a minute. So what we wind up doing is we can apply to each one of these different electrodes different voltages, and we can create kind of these waves inside that device. And by changing the orientation and the movement of these waves, we can actually move molecules through there. And some molecules, just like a surfer, might surf on the front of the wave, and others, if they didn't hit the wave quite right, they're going to roll over the back. And this is also a function of pressure and size. So to illustrate this a little bit more, here's a cross-sectional view of one of these boards here. It's a mirror image of what's shown here. But what's wind up occurring is that as we change the voltage, you can see how we can march that wave through the device, and molecules are going to wind up moving through this device. And so we can actually do some interesting work where we can stack these in tandem, and we can make very long path lengths. And in doing so, we have some nice separations that can occur. So this is a project that I'm pretty excited about. It allows us to get at a wide range of problems, like really just asking about fundamentals of separation science, but also looking at some other work related to structural biology and looking at how different proteins have different conformations as they are heated, as they are exposed to different types of gas phase species. And while this may seem as an esoteric problem or an idea, knowing what a protein's conformation is in the gas phase can also inform how you might model those in the solution phase. So lastly, we again are trying to exploit a range of ideas. This idea of selective ion chemistry is very important, whether it be charge transfer or clustering. This allows us to get at fundamentals, so this is looking at proton affinities of different gas phase clustering species, and also the idea where we can add certain modifiers to that gas-filled tube, create selective clustering applications, and separate out very difficult species. In this particular case, it was some chemical warfare agents, simulants, where we could see them separated when they were clustered, whereas if they were just exposed to the standard nitrogen gas, they wouldn't be separated.
What I'm interested in, I am primarily working with the nuts and bolts of chemistry, so stuff like instrument design, instrument assembly, some prototype evaluations, as well as some entry-level modeling work. So some of the stuff I've done thus far, I began by learning things such as soldering. I got to assemble some amplifiers. I got to do some basic 3D printing, which I found to be very interesting and very exciting, especially as you get better, you get to do more and more cool stuff. I've assembled some more complex electronics as time has gone on. I've got to install switches, work with wiring and stuff like that. As far as my project go, I'm primarily working with the SLIM. I'm not going to go into detail now. There are resources out there for you, but what I will say about it is we are one of the few groups working with that technique right now, and I think we are very fortunate and grateful that we get to do that. Something I want to let you guys know is that, all the stuff I mentioned, the printing, the soldering, all that stuff, I didn't know that when I first came here. The expectation is that you will not know that either. We are okay with that. We don't care about what you know now. We care about what you want to learn in the future. So if this interests you, please reach out. We are a very supportive group. We are small. We have a lot going on, which means a lot of opportunity for independent work, which I found, for me at least, and many others, is a great way to become a better scientist. And that's why you want to come here after all, is become a better scientist. So that's always good. While we do work often independently, I'd say we're still pretty close-knit. Dr. Clowers is a busy man, but he does come here often. He's always available for questions. We have a lot of grad students around. Even if we can't, answer specific questions about what you're working on, we're always good for sounding boards and his general support.
When I first joined the Clowers Group roughly 5 years ago, I had no idea what ion mobility spectrometry was. Never heard of it. And in addition, my mass spectrometry experience was confined to watching someone else run a GC with a quadrupole attached in undergrad. But since joining the Clowers Group, roughly within my first year of being in this group, we came into possession of the tracked ion mobility spectrometer behind me, which is a new-ish IMS device for our group with a quadrupole attached. But since I had the first couple of projects of my PhD on that instrument, my mind kept coming back to something that Dr. Clowers told me during my visitation here, which was the idea of measuring ion mobilities in defined mixed drift gases, which is something that no one's really done before. So during the last half of my PhD, I started that project, and along with that project, I've developed a couple of new skills as well that I didn't have upon entering the group, such as instrument design and how to solder and that sort of thing. So behind me actually is a new instrument design that we've been testing out this past year or so in the lab. It's incredibly easy to build. It's just a sheet of Kapton with electrodes on it, and I just solder a chain of resistors on there, and that establishes our electric field. Roll it up, you get your drift tube. But before then, we've been using these stacked PCB IMS designs, which is just a series of printed circuit boards just stacked together and then soldered together with a resistor chain with a top board. Other skills that I've learned since being in the group is public speaking and how to appeal to a broader audience, which is really demonstrated by the fact that I came in second for the College of Arts and Sciences 3-minute thesis competition last year. But these skills were built up through doing talks at conferences and presenting posters over the years as well. Our group tries to send people to national conferences at least once a year, sometimes more. Sometimes we go to regional ACS meetings as well. But that also gives us more exposure to what the field is like and more networking opportunities where we get to meet more people in the field. As for where I can see the direction of this group going, I can see my project being carried on a little bit after I leave, but I'm looking to graduate within 2 months, so I know that's not going to be a possibility. But the graduate students who are still here, that are younger than me, the second and first years, all of them have very varied and have incredibly varied interests. And they have different specialties and often go to each other before they go to Dr. Clowers for help. And they work really well together, so Clowers Group is a good place to be right now.
To my left, we have a typical setup for the Clowers Research Group. We have our PCB printed circuit board, eye mobility spectrometer, coupled to a mass spectrometer. For the experiments that I do in the group, I do hydrogen deuterium exchange. So the drift gas from the back of the drift tube travels to the front of the drift tube, and in that drift gas, we have a modifier that is a source of deuterium. So the hydrogen deuterium exchange reaction will occur within the drift tube, and we'll see the changes in the isotope ratio through the mass spectrometry data. When I started in the group, I didn't know a lot about what mass spectrometry or ion mobility was and what its applications served. But with just 2 years experience, I've learned a ton, and I'm really excited to keep learning and growing within the group. So one of the things that I didn't expect to learn in the group was to really understand how the instrument was built and how it works on a functional level. I was very interested in applications, but when things break on our printed circuit board eye mobility spectrometer, we have the ability to take it apart, figure out what's wrong with it, rebuild parts if necessary, and then get back to taking data. While a lot of the things that the Clowers Research Group are very diverse and very different, each of us have our own unique projects. A lot of the stuff that we do does overlap with one another, whether it be data analysis or things of that nature. So it's really great to see how everyone's growing and developing different things for their specific projects and how we can apply that to the rest of the group. So it seems like everyone is really a part of a team, and we have a really nice group dynamic. We're all working towards the advancement of research, and the successes of yourself and the successes of your fellow researchers are all wrapped into one thing.
The last question you might be thinking about, why WSU and why you should consider this as a place for you to spend the next couple of years. I was a graduate student here and also now as a professor. I very much like the area. I enjoy I'd say the feel of the campus, the camaraderie that's developed at the university. And I think that while it's surely not an urban campus, I think there's plenty of things to do. And if that's something that you're interested in, this is a great place for you. I think another thing that's really nice about Pullman and the surrounding area is that the summers here are fantastic. It's very hard to stay focused sometimes, but it's a nice balance between being able to spend a fair bit of time in the lab, focus on your research activities, but also then recharge when. So with that, I hope you strongly consider WSU as your destination for graduate school. Here in my group, we have a range of collaborations across the country. We have some strong collaborations with some NIH funding with Texas A&M. We have some active projects with University of Texas, University of Minnesota, and a range of other national labs. We also have some ties to industry as well, and that's one of the things that I think our program has some benefits where we have a broad range of opportunities for students both during their graduate career and after they've completed their graduate studies.